later. Now, a brief look at the Milky Way, our home galaxy. The Sun is just a tiny part of this giant galaxy, the Milky Way. The Milky Way, as a side view, this is the top view. Okay, side view looks like this. It's a giant disk, kind of thin disk. Thin, only relative terms, is about 2,000 light years thick or thin, however you look at it. But it's much greater across, which is about 100,000 light years across. Right? At the center of the Milky Way, there is a bulge. This is the bulge. And it's got a it's got a rotating structure like this, spiral structure, which is actually the whole thing is rotating, including our sun. Our sun is actually rotating. The sun is about 3/5 of the way out from the center. It's about 30,000 light years away from the center of the Milky Way. So from here to there, it's about half of that, which is 50,000 light years. So our sun is about 30,000 light years out. And our sun, along with the rest of the solar system, revolves around the center of the Milky Way. How do we know that? We know that by Doppler effect, by observing, the Doppler effect of the light emitted from other stars. We know how fast we're moving relative to them. Okay, it turns out with this data, you find that the speed of our sun moving around the center of the Milky Way is around 2.5 times 10 to the 5 meters per second. And you take that 30,000 light years as the radius. So the sun will spend about 230 million years for one complete revolution. This is called one galactic year, okay? Not one Earth year. One galaxy, about 230 million years. And we can also estimate the mass of the galaxy. Mass of the galaxy, at least the mass that's inside the sun, from this region to that region, okay? That's closer to the center of the Milky Way than our own sun. Using a very simple crude estimation, gravitational force between all this matter and the sun gives the sun the centripetal force, so m sun v squared over r. We know r is 30,000 light years. You do this calculation, you can find that the mass in our galaxy is roughly 2.7 times 10 to the 41 kilograms. That's a big number, but let's put it in perspective. This is about 1.3 times 10 to the 11 solar mass, which means if you consider all the stars to have the average mass of our sun in our galaxy, then our galaxy contains about 130 billion suns. 130 billion suns. That's roughly the calculation. Again, this is a side view, and since we are here, in our perspective, when we look at the center of the Milky Way, that's what we're going to see. So so in the night sky, the Milky Way appears to be a band of light. It's because of the perspective. Now, an alien can look from here or from above. Then when he looks from this way or that way, this is what he sees. Okay, we can never see something like that. This is not a real photograph, by the way. This is just an artist's rendition. The sun is roughly here. Here's the center of the Milky Way. All right, but when we did this calculation and we compare with the masses that we have measured, it turns out that the observed mass is only 10% of the total mass that we have estimated. So something is wrong here. Again, we have a problem. This problem is called the missing mass problem of the Milky Way. So we do not completely understand the behavior of our own galaxy. What are the possible solutions? Again, black hole comes to mind. A lot of scientists believe that at the center of our own galaxy, there is a massive black hole. It is not visible, therefore it's not counted in the observed mass, and yet it has mass, a huge amount of mass, which accounts for the difference. Another possibility, neutrinos may have mass. There are so many neutrinos, so they could make up the difference. And there are also those what's called WIMPs, okay? What does WIMP stand for here? Weakly interacting massive particles. That's what they mean, okay? Those are hypothetical. We haven't found them yet. But there are a few possibilities out here, and again, it's an unresolved problem at this point. Now let's talk briefly about stellar evolution. The sun is a main sequence star, like most stars, and it's middle-aged. But any star, including stars on the main sequence, will go through starburst, and then eventually when it gets old will die, which means it's not going to radiate anymore. And the the lifespan of a star go through different stages, and that's stellar evolution. We're going to talk briefly about stellar evolution. What is going to happen to our sun billions of years from now? When the sun exhausts its nuclear fuel at its core, the nuclear fuel at its core is hydrogen. Hydrogen fuses into helium. What if all the hydrogen in the core becomes helium and there is no fuel left anymore? Then what happens? Well, here is what we believe. Right now, that the sun, which is a main sequence star, is in hydrostatic equilibrium, which means the gravitational pull, which tends to collapse the star, balances with the radiation pressure due to the thermonuclear production of energy, burning the hydrogen at the center of the sun, producing helium. This produces an enormous amount of radiation pressure, which balances the gravitational pressure, so the sun is in equilibrium. Thank God, it is in equilibrium, at least right now. Okay, but again, later on, billions of years from now, the nuclear fuel at its core, which is proton, have exhausted, so you just got helium left. And then, so the nuclear energy production goes down, yet the mass is still there. Most of the mass is still there, so the gravitational pull continues. You have lost the balance. The gravitational collapse wins. So there is a huge amount of, there is a catastrophic event where gravity just pulls it in. It's called gravity-induced collapse. And when that happens, it makes a region surrounding the core denser than before. Okay, that heats up that surrounding region. That surrounding region still has plenty of hydrogen left. So the surrounding region starts to fuse. So you get new fuel. Okay, so you basically, the core is already dead. It's made of helium now, but that part around it start to fuse, and then what you get is a new round of nuclear fusion, and that's actually produced by this gravitational pull. And this new round of fusion event can dramatically heat up the star and making it brighter, and at the same time it will cause a shock wave to throw a lot of the matter out, so the star will start to expand. And as it expands, the surface, the outer region of the star will cool. I mean, even the sun today, the surface region, the temperature is only 5,800 Kelvin. And as it expands, even though the inside is still very hot, outside, as it expands, it cools down. It cools to about 5,000 Kelvin or lower. The color, therefore, is no longer yellow. It turns into orange and red. At the same time, the star, the outer surface expands because of the shock wave, and in the case of our sun, it's speculated that when it reaches that stage, it's going to engulf most of the inner planets, such as Venus and Mercury. Looks like Mars could be spared. It may not reach Mars, but the Earth, there are conflicting theories. It looks like the Earth may be engulfed by the sun as well, and the sun would just expand dramatically by about 200 times its current radius, and at the same time the surface temperature cools down, so it becomes red. So this is called a red giant. Okay, it's much bigger than before, but the color turns orange or red depending on surface temperature. This is an example. This is not our sun. This is an example of a red giant observed in 1997. It's from the Hubble Space Telescope, and you can see the color. It's a very distant star, so you don't see all kind of details, but this is an example of a red giant, and our sun eventually will become a red giant. That's the first step towards its process of death. Now, what happens next? Well, as the core continues to collapse, I mean, a lot of the matter got thrown out. I mean, for the case of our sun, about 40% of the mass got thrown out, but the core still is there, and the core starts to shrink and shrink. If you're not too massive, if you have a mass below 1.4 solar mass, if the core has a mass below 1.4 solar mass, the sun is of course an example, then what's going to happen is that it's going to shrink to about the size of the Earth. Okay, we're talking about 10 to the 7 meters, and we'll end up with as what's called a white dwarf. About 97% of the stars in our own galaxy will not be massive enough to pass that limit, and therefore 97% of our the stars in our own galaxy will eventually become a white dwarf. What's a white dwarf? First, we call it dwarf because again, it's a dwarf in terms of star size. We're talking about the size of the Earth instead of the size of the Sun. Okay, so it collapses because of gravitational pressure, but at some point it stops collapsing. It has reached an equilibrium. What's going on here? Well, first of all, proton will become helium at only this temperature, about 10 million Kelvin. And if the temperature gets higher, in the case of red giant, that can happen. You go to the 10 to the 8 Kelvin, then helium will also start to fuse, and you eventually get carbon and oxygen. That's the case for most white dwarfs. Some white dwarfs will start with greater mass. They can fuse even further to get magnesium and so on. But most white dwarfs are basically made of a whole bunch of carbon and a whole bunch of oxygen. Of course, don't forget electrons. Electrons are still there. Okay, but as they shrink to the size about 10 to the 7 meters, which is about the size of the Earth, the density of the white dwarf is so high that if you take a tablespoonful of material, the size of a matchbox, okay, from a white dwarf, and you bring it back and weigh it on the surface of the Earth, this little matchbox made of white dwarf materials will weigh an entire adult elephant. That's how dense it is. And this high density somehow stops gravity from further collapsing the star. It's going to stop at this size. What's stopping it? That's the interesting physics we're going to talk about. You know, we look at these candidates, okay? There's electron, there's carbon, there's oxygen. Out of these, this is the only one that's a fermion. Electrons are fermions. Fermions satisfy the Pauli principle. Now, if you put a whole bunch of fermions into a small region or denser region, which is the case for the electrons in a white dwarf, they cannot all collapse to the lowest energy state. They have to go higher and higher and higher in energy. They're squeezed into very high energy because of the Pauli principle, remember? Okay, so you go up to the Fermi energy, and that Fermi energy increases as the density of the electrons increase. In chapter 43, we learned EF equal to this. Okay, this for non-relativistic case, when the electrons do not move at relativistic speeds, we assume that's the case, and we go to this formula, n to the power 2 over 3. N is the number density of electrons. The number density of electrons is much higher in a white dwarf than in conventional materials such as a piece of copper on Earth. Here is the density of electrons in copper. We estimated that in chapter 43, and then this 10 to the 23 per centimeter cubed, it becomes 10 to the 30 per centimeter cubed. It's 7 orders of magnitude higher in a white dwarf. And since the Fermi energy is proportional to n to the power 2 over 3, that's a huge increase in Fermi energy. The Fermi energy can go from 8 eV in the case of copper to 300 kilo eV in a white dwarf. So basically, we're talking about an extremely energetic gas ball of electrons. And if you try to squeeze it even further due to gravitational collapse, gravity try to pull it further in, that's going to further increase n. But as n increases, n is already very large, as it further increases, the energy of the electron gas will be even higher. And who supplies its energy? The gravitational collapse. Okay, but even gravitational collapse only has limited supply of energy. You know, you lose gravitational potential energy, right? You give that energy to the electrons get more energetic. But the electrons are so incredibly energetic already that it's becoming more and more difficult to do that. So at some point, the pressure, the enormous pressure of gravity is balanced by the equivalent enormous amount of pressure due to the high density of the electrons. This is called the degenerate pressure. Degenerate pressure. Degenerate means the electrons are so close together, their wavelengths, their de Broglie wavelengths overlap. You cannot treat them as classical particles anymore. They must satisfy the Pauli principle. Okay, you have to consider their Pauli principle. So that is the answer to the question. What stops the gravitational collapse in a white dwarf? It is the degenerate pressure of electrons. It's a totally quantum effect. Totally quantum effect. So that's the nice thing about astrophysics. It actually provides us a stage to examine those theories of quantum mechanics, theories of gravitation, relativity, and gives an extraordinary stage because there's no way we can get that kind of a density and that kind of a, Fermi energy in any Earthbound laboratory, right? But here we have sort of like a celestial laboratory where all these enormous pressure can be realized, the density can be realized, and we can test our theory in these extraordinary cases. And it is reassuring, it's really nice to know that the theory that we learned by Earthbound experiment can actually work in those very remote places where humans would never set their foot on. That is the power of the theory of physics. All right, so again, when you squeeze the electrons, they become enormously energetic because of the Pauli principle, and it costs more and more for them to be squeezed even further. So at some point, gravity simply cannot do that anymore. So you achieve a balance. Here is a picture of a white dwarf, an actual white dwarf. This thing in the middle is not a white dwarf, okay? It is one of the two stars in a binary star system. Binary star is made of two closely spaced stars. It's called Sirius. Sirius is made of two stars because of the binary star. So this is Sirius A, which is very visible. It's a normal star. Where is Sirius B, you ask? Well, Sirius B is a white dwarf. It's much smaller, okay? And here is Sirius B. You see that little speck of light? This little speck of light? This is Sirius B. It is believed to be a white dwarf. Okay. Now, the exciting story of a supernova. Nova in Latin means a new star. A supernova is a very bright new star. And supernovas do not come up very easily, but they have been observed over the course of human history quite a few times. Here are a couple of famous ones. Here, this first one is called Kepler supernova. SN means supernova. 1604. What does that mean? It was first observed by people like Johannes Kepler himself. He was very lucky. He actually saw that during his lifespan. 1604. It was a bright star that just wasn't there before. It was a temporary star. It wasn't there before. Okay. This was the last confirmed supernova observed in our own Milky Way. This is a picture of this star today. It is no longer the same as Kepler looked at it, 400 something years ago. It is now a giant cloud of gas because this thing has expanded. This is what's left of Kepler supernova. It's enormous. And another famous supernova, perhaps the most famous of them all, is the Crab Nebula. This was first observed in the year 1054 by different people around the world, including the Arabs, the Chinese, the Japanese, among others. And the Chinese and Japanese have given detailed record of what happened. This thing, it was just a bright star, so bright you can see it in broad daylight. It appeared in this year, and it lasted for a little over a year before it disappeared. Today, because of the record that people kept, we knew exactly which direction to look for. So we trained our telescope in that direction, and guess what we found? We found this. It's called a Crab Nebula. It looks like a crab, at least to some people it looks like a crab. And it's got a region size of about 11 light years. It's huge. And not only so, it is expanding. Okay, it is expanding in all directions. At what speed? At about 1,500 kilometers per second. At that speed, if you trace it back, it turns out about 1,000 years ago, it would have come out from a very small region. That was that star that people saw, okay, which today has turned into this giant nebula. But at the center of that nebula is what remains of that star, which we believe is what's called a neutron star, which we'll talk about in a minute. Okay, so what's a supernova, and what caused it, and what's the physics? Well, a supernova typically it was a giant star with about 8 to 9 times solar mass. Because it's so big, its gravitational pull is more enormous than our own sun, and as the gravitational collapse takes place, the temperature can go to 10 to the 8 or 10 to the 9 Kelvin. Okay, and as a result, the nuclear furnace will keep on burning, which include nuclear synthesis of heavier elements, not just helium and carbon and oxygen anymore. You go to neon, you go to silicon, and on and on and on. In fact, you can go all the way to iron, number 26. The thing with iron is that iron is the single most stable nuclide. You cannot go any better. If you fuse anything into anything heavy than, if basically you take this guy iron, you fuse it into something else, you're only going to lose energy. You're not going to gain energy. Okay, so nuclear fusion will stop giving you energy once everything before that has been fused. This iron cannot be used as fusion material. Too bad. Okay, but the nuclear furnace still burns because the temperature is extremely high due to gravitational collapse. And there's so much radiation going on that the iron that's formed can actually absorb very energetic photons, and it will disintegrate back into neutrons and helium. The helium can further disintegrate into protons and neutrons, and this proton can form neutrons with electrons and so on. So the process can go backwards. All these processes are endothermic. They all take energy, and these processes are taking place in this as this giant star starts to collapse. Okay, and since these guys all absorb energy, that makes things even worse, and therefore the gravitational collapse will be accelerated, and that further enhances the process. So you have basically just a catastrophic event with the entire thing it collapses and sending a massive shock wave outwards along with a lot of energy, because the temperature gets so high, the nuclear energy production, fusion production rate gets incredibly large, so that for a brief moment, okay, we're talking about a few days or a few months or even a few years, this star can produce enough energy that its luminosity can be greater than the entire galaxy, but only briefly. Entire galaxy. Unbelievable. And this is where all the heavier metals, at least most of the heavier elements are made. When the star was formed, it actually already has trace amounts of heavier elements, pretty much all the elements, but it's mostly hydrogen, a little bit of helium. You wonder where these heavy elements are formed, say iron, such as silicon, or whatever we use. Okay, the calcium in our bone, where did they come from initially? Well, it turns out most of them are formed in a supernova event. Okay, so believe it or not, you and I, everybody, we are all made of stardust. Which star? Don't know, okay, but we're all made of stardust. So that's a supernova. So that's what we see. But at the center of the supernova, of this nebula, which is what's left of a supernova, there is a core. This core is what's called a neutron star. Look at this. Okay, because of photo disintegration, you end up with neutrons. So you have a whole bunch of neutrons, and these neutrons are closely packed because gravity pulls things in further and further. Nuclear fusion has stopped working to produce energy because we already reached this stage, and therefore gravity keeps on pulling it in. No nuclear fusion to produce any energy to counteract with it. What stops a neutron star from shrinking any further? Let's see. A neutron star is different from a white dwarf. It is even denser than a white dwarf. The mass of a neutron star should be at least 1.4 times the mass of the sun. If you're below that mass, then it's not going to form a neutron star, which just end up at the white dwarf stage. But no white dwarf can exceed 1.4 solar mass. This is the famous Chandrasekhar limit calculated by Chandrasekhar. If the mass is greater than that, then the white dwarf, the degenerate pressure from the electrons, will not do a sufficient job to stop collapsing from going on further, and you end up becoming a neutron star. If the mass is not more than 3.2 solar mass, okay, if the core, that's what's left. So between this mass and that mass, you're going to have a neutron star. A neutron star is so dense that you start with at least 1.4 solar mass, and you end up with a core of neutrons the size of several kilometers, a small city, several kilometers instead of the size of the Earth. At the center of the Crab Nebula, we believe there is actually such a neutron star. It's got a diameter about 30 kilometers, It's called a Crab pulsar, which we'll talk in just a minute. The density is that of nuclear matter. We saw the density of nuclear matter already, 10 to 17 kilograms per meter squared, per meter cubed, right? This is an enormous density. I mean, we talk about that, right? I mean, you take a matchbox and, how many of these giant ships do you have to carry them? It's just enormous, okay? At this enormous density, neutrons, remember neutrons are fermions too, right? Neutrons will get so close together that their Fermi energy skyrockets. And you repeat the same story as white dwarf, except we're using much denser neutrons to replace these electrons. The neutrons will have such an enormous amount of degenerate pressure that even gravitational pull cannot go on forever. It will stabilize when a bunch of neutrons form a neutron star. Again, at this point, there is no radiation going on anymore. Through nuclear fusion, there's no radiation. So it is the degenerate pressure from the neutrons that stop the gravitational collapse. But the neutron star can still spin because of conservation of angular momentum. We can do a little estimation. Conservation of angular momentum. Okay, so as it gets smaller, it spins faster and faster, right? Okay, the rotational inertia is roughly proportional to radius squared, and omega is 1 over t being the period. We can estimate the period of a neutron star as it shrinks from the size of a large star to the size of a few kilometers. How much faster would it get in terms of its own spin? Well, we can use our sun as a crude estimation. The sun is not going to be a neutron star. It will just become a white dwarf, but we can use that roughly to do an estimation. This is the final size of a neutron star. This is the initial size, using the sun as an example. The initial period of our sun, the time it takes for the sun to revolve around itself, it's about 30 days, 30 Earth days. Okay, so about 10 to the 7 seconds. You do this calculation, you find the neutron star will have an incredible period of a fraction of a second, 10 negative 3 seconds. It spins incredibly fast because of conservation of angular momentum. In the case of Crab pulsar, when we look at the radiation from Crab pulsar, we find it's got a period of 0.033 seconds. This is only to the first two sig figures, but this in fact is a highly stable period, okay, or highly stable frequency. This frequency is so incredibly stable that this will give us the most accurate clock in the universe. It's more accurate than anything that we have made on Earth to keep time, including the best atomic clock. The reason why it's so highly stable is because of conservation of angular momentum. As a matter of fact, this frequency was so incredibly regular and stable that initially people thought that they just discovered some extraterrestrial intelligence, some aliens doing that, but it turns out it's just a phenomenon of nature, conservation of angular momentum. All right, now, finally, black holes. You start with a neutron star. It's got a lower mass limit of 1.4 solar mass and a higher mass limit about 3.2. What if you have a more massive core, greater in mass than 3.2 solar mass? What happens? Even the degenerate pressure of neutrons cannot stop the gravitational collapse. And there is no other known mechanism at this point, at least, that can stop the collapsing from happening. So gravity has no enemy anymore. Okay, so the collapse will continue until it shrinks to virtually a point. That is called a black hole. It still has its mass, but the size reduces to 0. Now, how far do we must stay away from the center of the black hole so that we'll not fall in? Well, light, as you know, travels faster than anything else, so it's got the best chance of escaping. But this is how you calculate the escape speed, right? 1 half mv squared equals gmm over r, assuming it's non-relativistic. The more massive the star is, the higher the escape velocity, okay? But what if I set escape velocity all the way to c, the speed of light? I mean, nothing can go faster than that, right? And from that, you can replace this v escape with c and calculate this r. This tells you that if you have a mass m, okay, and you are this far or closer than this mass, this is called Schwarzschild radius, then even if you are a photon, you still cannot escape anymore because it would require escape speed greater than that of light, which is not possible. This is called the Schwarzschild radius. So imagine something collapsing to the size smaller than that, nothing can stop it. Keep on collapsing. Even light that's getting within this distance from its center will be sucked in. Black holes can absorb light that way. And as it absorbs energy, it will become bigger and bigger and bigger, not in size, but in terms of the Schwarzschild radius. Okay, so it will be more and more dangerous, more and more massive. Now, we're dividing everything by c squared, so it's a very small number usually. Even if you take m as one solar mass, okay, one solar mass, the radius of the Schwarzschild radius is only 3 kilometers. In other words, if a beam of light gets within 3 kilometers away from that from the center of that black hole, it will be absorbed, but that's a pretty small distance. So we have heard scientists in their study of controlled nuclear fusion, they want to create a miniature black hole, sort of, by shining powerful beams of light onto a drop of water, and to collapse that drop of water to extremely small size, smaller than Schwarzschild radius, and then what you get is it's going to shrink by itself to a tiny, tiny, tiny black hole. Okay. Now the question is, that black hole, could it absorb the matter around it and become bigger and bigger and bigger, and there's no charge on it? Then you cannot use electrical force to control it, right? So it's going to be moving toward the center of the Earth due to the gravitational attraction, and it's going to pass through the center of the Earth and will just oscillate back and forth, as it passes by the center of the Earth. And as it does that, it will continue to absorb more matter around it, grows bigger and bigger and bigger. Eventually, can it absorb everything on Earth so that the Earth will not exist anymore? Okay, that sounds very scary, right? But if that's what scientists are doing, then they should be stopped. Of course, the scientists know what they're doing. Okay, this hypothetical scenario does not work. Even if the scientists succeed in creating a miniature black hole, it is not going to do any harm like this to us, because you have to look at the Schwarzschild radius. Even for the mass of the sun, we're looking at 3 kilometers. The mass of the Earth will be much, much shorter, much, much smaller. And if you look at a 1 gram, say a 1 gram mass, if you collapse that 1 gram of water into a miniature black hole, its Schwarzschild radius, you can do a little calculation. 1 gram, let's say 1 kilogram. Let's be generous, okay? We don't have the technology to do that, by the way. 1 kilogram versus the mass of the sun, which is 10 to the 30 kilograms. The Schwarzschild radius, we're looking at 30 orders of magnitude lower than that. That is 10 to the negative 27 meters. How does that compare with the size of a proton, which is 10 to the negative 15 meters, or 1 Fermi? The Schwarzschild radius is many orders of magnitude lower than even the smallest matter that we know. And therefore, unless you get that close to it, which is impossible, okay, it's not going to swallow you, and therefore this tiny little black hole is not going to do anything to us. Okay, but it's really interesting. Black holes are among the most fascinating subjects in our scientific study, and also even in popular culture. What we have here is a artist rendering of the gravitational lensing effect. You put a black hole in front of the large Magellanic Cloud, which is a nearby galaxy. The Magellanic Cloud is behind this black hole, and we look towards it with the black hole in the middle. The gravitational effect of this black hole will literally bend light. So you have a light source from here. You do not travel this way anymore. As light gets close enough to the black hole will bend it around it, even though it doesn't absorb it because you're still not as close as that. But it's powerful enough to bend the light. So these two beams will reconverge here. It's like a lens. Okay, so you actually see something there, and you actually get two distorted image of the same cloud. And the Milky Way in the distance is also bent. The image is also bent because of the gravitational lensing effect. We cannot see black holes directly, but there are things that we can observe around black holes, such as when it sucks in matter from a nearby star, it can create radiation that we can see, that sort of thing. Even though there are no concrete evidence, no indisputable evidence that black holes exist. Most scientists believe they do, because you can use them to explain so many things.